All right, good afternoon. So first things first, there is the warm-up question on the screen. So we want to make sure that you guys are working on that warm-up question. I want to give you guys a little bit of time to work through it. So make sure that you guys pause the video so that you guys can work through it and then come back to the video when you think you've got an answer so that you can check your work. Hopefully there's still some stuff left on the screen, but if not, that's totally fine. We'll go ahead and work through these problems together. All right, so here is the solution for the first part of the warm-up. So the way that we can kind of figure out how good the data is to kind of look at the uncertainty of it. So the first thing that we're going to do is we're going to look at the data, right? 12, 14, and 16. And we're going to ignore the middle number. We're really just concerned with the highest and the lowest, so the 12 and the 16. So what we want to do is we want to find the middle of that. Now it just so happens to be 14, but it doesn't usually happen that way. So what we're going to do is we're going to add together the minimum value, the 12, and the maximum value, the 16, and then divide that by 2. So 12 plus 16 is 28. 28 divided by 2 is 14. So it just so happens that that 14 was the middle. The next thing that we're going to do is we're going to kind of see how far away our values are from that middle value. And so we're going to take that maximum value, 16, and subtract off the middle value that we just calculated. So 16 minus 14 is 2, so they're 2 apart. And then we can write it out as our middle value plus or minus the uncertainty. So 14 plus or minus 2. And this tells us all the possible values that fit our data set. So if we take 14 plus 2, we get the highest value of 16. If we take 14 minus 2, we get 12, the lowest value of our data set. And then all of our other data should be somewhere in the middle of that, somewhere between the 12 and the 16. All right, so we're going to go ahead and take a look at the next one as well. So this time, again, we're doing the same thing. We're going to ignore the 12.9. We're just looking at the lowest possible value, 12.5, and the highest possible value, 13. So we're going to add those together. 12.5 plus 13 is going to equal 25.5. When we divide that by 2, we get 12.75. So 12.75 is in the middle of our data. Notice that it's not actually one of the data points. That's okay. The next thing we're going to do is look at that uncertainty. So we're going to take that maximum value, 13, and subtract off that middle value of 12.75. And we're told 0.25 is how far apart these numbers are, which is great. Now we can look at how we would write this out, and it's that middle value, 12.75, plus or minus the uncertainty value of 0.25. Again, it's always really good to double check, make sure that it does cover your highest and your lowest values. So if we take 12.75 and add 0.25, we get 13. If we do 12.75 minus 0.25, we get down to 12.5. So that's the highest and the lowest, and then everything else should be somewhere in the middle of that. Perfect. So now we get back to our question that we had at the beginning, which was which set of data is better than the other. Now, better may not be the best word choice here. We don't know what the actual answer is supposed to be, so we don't necessarily know which set of data is better, but we do know which set of data is more precise. Notice that in the first one, we had plus or minus 2. Notice that the second one, we had plus or minus 0.25. So that second set of data, set B, is much more precise, meaning that all of the values that we measured were all closer together. Now that tells us that we're probably more consistent with how we're collecting that data. We're more accurate with whatever measurements we're making and things like that. So this is a better set of data in terms of accuracy, or in terms of that precision, and making sure that we are getting similar values each and every time we collect data. All right. Last time, we may or may not have gotten to filling in the controls and the qualitative data for our lab write-up. So if you have done this part already, that's okay. Just skip past this part of the video. If you haven't, make sure that you guys do get going on this part. So let's take a look at this together. All right, so you'll want to go to the Google Classroom and open up that template for Pendulum. And if you were not here last time, then you're probably missing all the other stuff above this data table as well. So you'll want to look at the slides that are provided, and that's in the Google Classroom as well. It's not an assignment. So what you'll want to do is click on the classwork tab at the top, and then just go to the class materials. And in the class materials, there's a Unit 1 Patterns Google Slides. If you open that up, you'll have a big old table of contents that you can click on. You'll want to use the September 6th and 9th Pendulum Lab 1 link, and that's going to get you to the slides where we started talking about setting up this lab. And it'll kind of walk you through like how we thought about the system, the pendulum, how we asked some questions about it, and then how to start filling some stuff in, like what is the wild guess question? Obviously, the wild guess answer is what you think the answer is to that question. And then how to word something like a research question, where we can turn that wild guess question into something that we can actually study, right, with an independent variable and a dependent variable, and hypothesis, and so on and so forth. But for now, we're going to go ahead and scroll down and look at the data collection part. So the controls, if you didn't do this last time, the controls are the things that we want to keep the same from trial to trial. So when we swing that pendulum, what do we want to make sure stays the same? So I'll give you guys some time to think about that. Write down what you think should stay the same. For the qualitative data, this is going to be the things that we observe when we do the lab. And since you guys aren't going to be doing the lab, you're just going to be looking at the data that was collected. There's a couple of things that we can put in here for the qualitative data. The first is that when we add a mass to the string, it starts to spin. Just on its own, it starts to spin. So that's something worth noting. It's not data that we would put into our data table or anything like that. It's just an observation that we're making that may or may not have an impact. So we want to make sure that we note it. Another thing is when I let go of the pendulum and it starts to swing across, it wobbles a bit, it shakes a bit. Again, don't know if that has anything to do with anything, but it's worth noting so that somebody else could go ahead and do a study later on to see if it did have an impact or not. And then we want to set up our actual data table itself. So we've got the column that says IV, and it has 10, 20, 30, 40, 50. Well, if we remember what our independent variable is, right, we can fill that in. If we don't remember, we can always scroll up a little bit and look and see what it says for the independent variable. Now, this is going to be the part that we're looking at the x-axis here. So if you filled in your hypothesis correctly, you could look at the x-axis there. It's also in our research question. So if you did the research question, it should be there as well. But we basically want it to have starting angle, Now we're also going to put degrees in there just to identify the units that we're going to be measuring the angle in. And we have a little plus or minus 5. And that just helps show that my accuracy might not be perfect. When I line it up and think that it's 10 degrees, it might be a little bit less. It might be down to 5 degrees or as much as 15 degrees. But that plus or minus 5 just kind of goes to show my lack of accuracy, right? The thing that I'm using to measure it is way up on the ceiling. So I'm trying to eyeball it from way down on the ground, line things up as best I can, but I'm not going to be perfect. And that just helps to kind of mitigate some of the issues that might be there. The next thing is the dependent variable for that next column. And again, it should be up in your lab earlier on. It's the y-axis in your hypothesis. It also should be in your research question. And the dependent variable is the average time of one complete swing. Now the units we're going to be using are seconds. So again, we'll just put that in parentheses. You can just put an S. If you want to write out seconds, that's fine as well. And then we have plus or minus 0.3. And again, this kind of goes into your reaction time when you are clicking the start and stop, your hand-eye coordination of when you think that it gets to the highest point and then clicking the button, things like that. So again, just shows that we know that we're not 100% perfect with everything, and that's okay. And we just want to make sure that we're showing that when we are collecting our data. So hopefully you have finished your table, and it should look something like this. Again, starting angle already filled in. Dependent variable is the average time of a swing. And again, we're going to go ahead and fill this in. Now, we had mentioned before that we're going to let it swing for 3 times and then take the average, meaning divide that by 3. And the question is kind of why would we do something like that? And the reason for doing that is to reduce the impact that our reaction time has, right? So say we're off by half a second. If we're off by half a second when we time things and we only let it swing once, then our measurement is half a second off of what it should be. If we let it swing 3 times, we're still half a second off, but when we divide by 3, it cuts that half second error into thirds, right? And that makes the error that we're introducing even smaller. So obviously it would be even better if we did like 10 swings or 100 swings or 1,000 swings. But we start introducing other errors, right? Making sure that we're keeping track of the count. 1,000, that's a lot, right? We might lose count by then. Or we have to worry about things like the introduction of air resistance, right? A couple of swings, no big deal. But 1,000 swings, right? There's a lot more air resistance that would have an effect. And so we don't want to have to worry about other errors. So 3 is a kind of good, safe number that helps reduce it a bit, but doesn't introduce too many other issues or errors. All right, well, we need to kind of fill this table out. And so we'll kind of look at the data from the students yesterday and what they collected. And so this is what this looks like. And so we have all the data that they collected. And it's even more than this, right? There's some more students off to the side here. But this is plenty. And you'll notice that a couple of these spots are blank, right? And that's okay. That just tells us that when they were trying to collect the data, maybe they misclicked, right? And they know that their time is off, so they're not going to record it. But then everybody else was clicking and recording the values. So if it's blank, it's just because they were unable to get a time for that trial. And that's totally okay. Again, you'll notice the range of the data set. So our range increased a bit as we went. And that just kind of shows that it's a little bit harder as we go. It's a little bit harder to get an accurate measurement of what the highest point is in the swing. And so some people were a little bit early when they thought the highest point was. Some people were a little bit late and it started coming back down before they clicked it. Again, it happens, right? It's harder to do as the angle gets bigger. So our range of the data increased a little bit. We had it pre-calculate for us the average of the three swings. So it's taking all of the data that was collected, right? Ignoring the spots that were missing, and then averaging it, adding them all up, dividing by however many people were able to get a trial, and then getting that for the average of the three swings. And then over here on the left-hand side, this is where we're actually going to be looking. This is what we're going to put into our data table. These are the average time of one swing. So it's basically just taking the average time for the three swings and just dividing that by 3 to get one swing. And we can see that 2.8, 2.8, 2.8, 2.9, 2.9. So we're going to go ahead and take that and fill it into that data table that we have here. So 2.8, 2.8, 2.8, 2.9, and 2.9. So now your lab is getting a little bit more complete. You'll notice there's a spot underneath the 50. And then we just leave that for now. That's totally fine. We're not going to worry about that. The next thing we're going to do, though, is we're going to want to go ahead and do some Desmos graphing. And this data table right here in front of us, this is what we're going to go ahead and put into Desmos. So we'll kind of step through how to do some of those things. All right. Again, at the very top above my whiteboard in the classroom, there are steps, right, that help us work through how to graph Desmos. So if you ever forget, you can always look up there. You can always come back to this slide. First step, input our data. So on your lab, it has a link to the Desmos. And if you click that link, it'll take you right to that Desmos graph. And in the upper left corner, it has an empty data table. And so we need to go ahead and fill in that data table. Now, it is set up with 2 columns, an S and a T. Well, the 2 columns that we have from our data table, we can kind of try and figure out which one makes sense where. S for starting angle, T for time. And so we can go ahead and fill in our starting angles and fill in the times that match that. All right. The next thing, once we've put in that data, is we want to choose the best fit line. And the way that you do that in Desmos is there's a little C slider. It's sort of the spot number 4 if you are looking at Desmos. Basically, there's just like a little dot, and then you can click and drag that dot around. And as soon as you click that dot and start dragging it, you'll notice a bunch of colored lines pop into existence, right? If you just move it a little bit, you'll probably notice that sort of red diagonal line jumps out at you. And it might go through like one of our points, but that's not a good fit. And so what we really want to do is we want to keep sliding that slider until one of these lines actually starts lining up with our data. And it turns out that the black line is the one that's going to line up the best. And so again, you can slide it until you think that that C value lines up nicely with all of the data. And for me, that's somewhere in the 2.8, 2.9 range. All right, now that we've got the line that we like, we're going to go ahead and remove the colored lines that don't fit. So we don't like the red line, right? We don't like the blue or the green line. So on the left panel of Desmos, you'll see sort of these red dot, blue dot, and green dot with like a squiggle through them. And if you just click on the red dot, it'll just make that line disappear. Click on the blue one, makes that line disappear. Click on the green one, and that one is gone as well. So now we should only have that nice black line. And we're going to write in our mathematical model. So in order to do this, again, we're kind of looking at the line that we used, right? Not the red line, not the green line, or the blue line. We're looking at the equation for the black line. And the equation for the black line is T equals C. T equals C. And that's all well and good, but we want the mathematical model to be in words. So we're going to replace each of those parts. So instead of T, we need to think back to what is T, right? In our data table, what is T? Time of one swing, or average time of one swing, is what we'll want to put in there. So time of a swing, and then we need to now replace the C. And we can think, well, I don't know what C is. It's not part of my data table. And it's not. But what it is it's from the slider, right? We slid it until the C value was 2.9. And so we're going to put in 2.9 for the C. So what it should say for our mathematical model is something like time of one swing, or average time of one swing, equals 2.9, or 2.8 if you thought 2.8 fit better. And that's what we should have for our mathematical model. So this time our graph should be looking really nice, right? We've got our data points, our 5 data points with little boxes around them. We've got our black line that goes through almost all the points. We've got our equation that says time of one swing equals 2.9, right? We've got all the pieces for this really nice graph. And then what we want to do is save that graph. So if we take a screenshot of it, Control Alt, and then there's like a button like above the 6 or something on the Chromebook. Again, if you look on the wall right above the whiteboard, it kind of shows what that symbol looks like. It's like a box with some lines. Either way, take a screenshot of that graph and you're going to paste that screenshot into your lab write-up. Now, a couple of things that we want to make sure are part of this picture that we're taking, this screenshot. We want to make sure that the axes labels are there, right? Time of one swing for the y-axis, starting angle in degrees for the x-axis. We need to make sure that those are part of the screenshot. Obviously, the data needs to be there and the mathematical model needs to be there. So make sure all those parts are in your screenshot. And then, of course, paste that screenshot into the lab. All right. So again, our graph should look something like this. Obviously, the C value is going to be a bit different, right? Probably not 2.5. It's probably 2.8, 2.9, 2.85. Some people decided to put kind of whatever, right? Your data table is going to look different. That's okay. But all of this other stuff is what we want to make sure is in our screenshot, right? We don't care about the left panel, right? It shows the data, which is fine, but we already have a data table for that. shows the C value, but we don't need that because it's going to be in our actual graph screenshot. All right. Now we need to identify what type of pattern this is because this is what's going to help us write our conclusion. Right? And that's the next part, is writing our conclusion. So if we look at the 4 patterns up on the wall, or if we look at the 4 patterns in our notebook, we should hopefully be able to identify that this is in fact a horizontal line. And if we look at, oops, if we look at that horizontal line, right, this is what we're looking at. It's not perfect, right? Some of the data might be a little bit above, might be a little bit below, but for the most part, that value didn't change when we were collecting the data. So what is this telling us? Well, it's telling us that the x value, when we change it, right, when we change the angle of the swing, it doesn't actually have any effect whatsoever on the y, which is the time of a swing. So doubling the angle didn't double the time, right? The time basically stayed the same. Going from 10 degrees to 20 degrees, the time didn't change. Going from 20 to 40, still didn't change. And so this is why we're looking at this as a horizontal line. We might have thought that the angle was going to have an impact. Turns out it doesn't. That's okay. So again, when x doubles, y stays constant, right? Our y value never changed. Our time of a swing didn't change. So this is one of the 4 patterns that you should again have in your notes. All right, well, now we're going to go ahead and take a look at our conclusion and writing our conclusion. There are some blanks that we need to fill in, and so that's what we're going to be looking at, is filling in those blanks. Now, a really nice thing is that this conclusion, right, we can kind of use this to fill in for other labs as well, right? After investigating the behavior of blank. So what were we investigating the behavior of? Well, we were investigating the behavior of a pendulum, right? So after investigating the behavior of a pendulum, I conclude that there is a blank relationship. So what kind of relationship, what kind of pattern did we notice between those 2 variables? Well, horizontal. And you'll notice that this whole beginning part here is red, right? This is our claim. This is our claim. This is what we think is happening. And that claim is all in red to help you guys kind of identify what part of the conclusion you're working on. It also helps me with grading to see, oh yeah, they did their claim. Great, give them full points. You'll notice that the parts in blue where you guys are typing, right? A lot of times when you type the pendulum, right, behavior of the pendulum or horizontal relationship, the words that you're adding in there are blue. And again, that makes it easier for me to look and make sure that you guys did in fact fill in the blanks and type in the parts that you needed to type in. So if it's blue, right, just leave it that way. That's fine. Now we get into the independent variable and the dependent variable. So again, remembering that they're scattered across your lab and you can always look these up if you forget what they are. They should be in that data table right above it. They should be the axes for your Desmos graph. So you can look there as well. But we've got the horizontal relationship between the IV independent variable, which is the starting angle. and the dv, the dependent variable, which is the average time of one swing. And that's our claim. Our claim is that we investigated, we looked at the behavior of a pendulum, we realized that there was a horizontal relationship between the starting angle and the average time of one swing. So now we need to get into our evidence. And that's where this sort of orangish yellowish color comes in. My evidence for this claim is that all of my data fits on a best fit line that is, what was that pattern again? Horizontal. As the starting angle kept increasing, the time of one swing stayed at the same value. Right? Our times didn't change. This system of again, what was the system again? Pendulum, can be mathematically modeled as, this is where we want to use that really generic equation from Desmos, right? Before we started putting in all the other parts to it, we just want the kind of generic one where it's just T equals C, right? T equals C, where the constant, the C value, 3.1, is the time of one swing, right? The constant C value, 3.1, is the time for one swing, or average time for one swing. That's fine. Additionally, it makes sense that the pattern is, what was the pattern? Horizontal. It makes sense that the pattern is horizontal because, and again, we have to get into the reasoning. Well, we're just saying that changing the angle didn't change the time, right? Changing the angle didn't change the time at all. Last but not least, we have our prediction area. And again, this goes back to the question that we asked at the very beginning. Using this model, I predict. Well, we want to answer that research question. I predict that the time for a 60-degree swing angle will be 2.8, 2.9, whatever you found in your equation. Because again, we remember that we realized that the angle didn't impact the time. So it doesn't matter if it's 60 degrees or 70 degrees or 10 degrees. The time is going to be the same. All right, so I'm going to read through that whole conclusion again. For the most part, you should have what I've got. You might have some different word choices here or there. That's totally fine. After investigating the behavior of the pendulum, I conclude that there is a horizontal relationship between the starting angle and the time. My evidence for this claim is that all of my data fits on a best fit line that is horizontal. As the starting angle kept increasing, the time of one swing stayed the same. This system of a pendulum can be mathematically modeled as T equals C, where the constant C value, 3.1 or 2.8 or whatever you had, is the time for one swing. Additionally, it makes sense that the pattern is horizontal because changing the angle didn't change the time. Using this model, I predict that the time for a 60-degree swing angle will be 2.8, 2.9, whatever you have. All right, almost done. One last thing is the research extension question. So this is where you guys have to think of something else that may or may not have an effect on the pendulum. What else could we have studied? Instead of angle and time, what's something else we could have done? Well, if you get stuck on this, if you're unsure, a really good place to look is the controls that you set up earlier. What are the things that we wanted to make sure stayed the same? Because these are things that we can now change. We said we wanted the mass to stay the same. Well, how does changing the mass change the swing time? Boom. That's a research extension, right? Or we said that the string length needed to stay the same. Okay, how does changing the length of the string affect the time? We said number of swings, right? We were timing 3 swings and taking an average. Well, instead of taking an average, we could just do it for 1 swing, time it. Do it for 2 swings, time it. Do it for 3 swings, time it. Is it going to increase the time as we increase the number of swings? Yeah, probably. But that's okay, right? How will changing the number of swings affect the time? Perfect, right? A lot of different ways that you guys could fill in that extension question. In fact, I like doing that extension question early on. Like as soon as we're starting to talk about the system, we're brainstorming all those different ways that we could do tests on the system. That's when I like to do the research extension, because that's when we're thinking about all these things. All right. So double check that you guys have everything done, right? You want to make sure that you go back up to the top of your lab and that you're scrolling through it and you don't have anything that says click here to type. The areas that people often miss, where it says performed by, right? A lot of people forget to type their name in there. A lot of people forget to fill in the click here to types for the hypothesis graph form, right? So you want to make sure that you have those axes labeled. It's the same as the Desmos axes, so you could always look there if you get stuck. It's color coordinated to kind of match what we had up on the screen and what we were using with you guys for the dependent and the independent variables. So make sure that you guys have all of that stuff filled out. Make sure that your hypothesis words match your graph. If you think it was going to increase, right, then your line should increase going up. If you thought it was going to decrease, your line should decrease. And if you thought it should stay the same, then your line should just be a horizontal line that goes across. Now we know the answer at this point, but don't go back and change those things, right? It's okay if your hypothesis was wrong. It's okay if your wild guess answer was wrong. It probably was. That's okay. The point is that we wanted to get better after collecting data. So hopefully your prediction now is much closer to what it really is than your wild guess. And in class next time, we'll go ahead and set it up and we'll swing it from 60 degrees and we'll see how close our answer was. All right, if you guys have finished all this stuff, make sure that you guys are double checking that you turned in all of the things for this class, namely the Get to Know You survey. Also, the other day we had the worksheet that we taped or glued into our notebook. If you need one of those, there are extra copies of that worksheet at the front. And that was the variable worksheet where we practiced thinking about what the independent and dependent variables were, what some of the controls should be, things like that. So if you're missing any of that stuff, make sure that you guys are being responsible and getting that collected. If you are completely done with your lab, make sure you get that turned in. Make sure you do keep your phones away throughout class, and you can, in fact, work on something for another class. So if you have some social studies work that you need to catch up on, go ahead and work on that. I know that you guys always have math homework, so feel free to work on what you need to work on once you've finished the lab. All right, have a great day.